Okay, so good afternoon and welcome to lecture number 23. In last lecture, we have completed our third chapter. In this lecture, we will start chapter number 4 according to our syllabus. And the title of this chapter is Time Domain Analysis of a Control System. Okay, so in this chapter, we will be studying basically what are the basic, what is by time domain analysis, and then what are the different standard test signals which are used for doing the time domain analysis, and then response of first order control system, response of second order control system, time response of second order control system. So in that we'll see various time indices, like for example, that in time response there are two parts of time response, one in transient part and another one is a steady state part. So whatever is there that we are going to study, so in transient response part, basically there are indices like for example peak time, rise time, delay time, and then settling time, and then maximum peak overshoot. So we'll see what are all those terms. And then in steady state part, what is a steady state error. So steady state error for different types of input, but how steady state error changes by changing the input and so on. And then in the last, at the end, we will study the steady state error part particularly. Okay, so in that we'll study error constants, and then errors and error constant and so on. So that is what we are going to study in this chapter, as well as we will be studying at the end we will be studying different types of controllers, like on-off controller, then integral controller, derivative controller, and this one PID controller, and so on. So that will be the last part of this chapter. Okay, so let us look at this one, the first part of this chapter, that is introduction about time domain analysis. See, what is by time domain analysis? Means basically when you know that what is by time domain. So when you are plotting the output, okay, you will be plotting that output with respect to some independent variable. Okay, so this independent variable is generally taken on the x-axis, and on y-axis that response is taken. Okay, so this independent variable, if it is time, okay, then it is called as the time response. Okay, if it is frequency, then it is called as the frequency response. So you might have seen the graph, like for example in graph there are two axes. One axis is x-axis and another axis is y-axis. So in x-axis generally, okay, you have taken a independent variable, this one, as a time, and on y-axis the response of that system is. So when you are plotting the response of that system with respect to time, okay, and then you are doing the analysis of that system, so that overall picture will be a time domain analysis of a control system and so on. Means how that control system behaves with respect to time for a given input. So that analysis is nothing but the time domain analysis of a control system. So from this time domain analysis, we will come to know whether that system is really fast or whether that system is sluggish, how much time it takes to reach the steady state value, is there any error in the output of that system. So all those parameters we are going to study. Means once you have designed the system, we have to test that system for various input and so on. Here in the time domain analysis, the response of a dynamic system to an input is expressed as a function of time. Means you are taking the your x-axis is time and y-axis is a response. So independent time is independent parameter, and okay, you'll be doing the analysis of that system with respect to time. So that is called as the time response analysis and so on. And it is possible to compute the time response of a system if the nature of input and the mathematical model of the systems are known. Means what kind of input is given, what kind of system or system is there. Like for example, if you know the transfer function of that system and if you know the input, then you know that, okay, what is my transfer function? It is the ratio of Laplace transform output variable to the Laplace transform input variable. So if transfer function is known, if input is known, then you can easily calculate the value of output or time response of that system or output response output of that system and so on. So it is possible to compute the time response of a system if the nature of input, means what kind of input is given, and then what is the mathematical model of that system, that is nothing but your transfer function of that system. If transfer function is known and if input is known, you can easily calculate the response of that system and so on. So usually the input signals to the control systems are not known fully ahead of the time, right? So so it is therefore difficult, difficult to express the actual input signal mathematically by simple equations. And generally, you know that when you have designed a control system, you have to test that system for any worst case. Like for example, you have designed a car or any vehicle. So what happens basically, how that vehicle should be tested and so on. So those students, those who are involved in BA project, okay, along with the mechanical department for designing the all-terrain vehicle, so they might have tested that vehicle for all those worst conditions. Like for example, if you apply a sudden brake, what will happen to that system? Okay, if there is a constant velocity, what will happen? If there is a constant acceleration, what will happen? Like or if there is a sudden shock to that system, what will happen? So all those worst cases, for worst cases, we should test that system, and if that system sustains those sudden shock or sudden change or constant velocity and constant acceleration, if that system sustains those changes, then that system can be deployed for the real world application and so on. So how to test all those things in a laboratory? So you know that as I said that if you give the sudden shock, so is there any signal which will represent the sudden shock? Or like for example, if you give the sudden change to that system, like for example, if the system input are 0 and all of a sudden it has been given like as a 500 as an input, so there is a change of 500, so sudden change is there. What will happen to that system if you give the sudden change? And then if you are increasing a velocity of the input constantly, what will happen to that system? Or if you are increasing the acceleration of input constantly, what will happen to that system and so on? So we'd like to do the analysis of that system based on the sudden shock or sudden change or sudden constant velocity and constant acceleration. So how to do all those things in a laboratory to test that system? So there are basically electronic signals which represents this this kind of characteristics, like for example, sudden shock. So you might have seen the impulse response. So what is the impulse input? So impulse input is basically, it has the magnitude equal to infinite when t equal to 0, and at the rest of the time it is 0. So you are giving suddenly shock to that system, like for example, infinite input at t equal to 0, and below t equal to 0 or above t equal to 0, your input is 0. So this kind of input is nothing but a sudden shock, right? Or like for example, sudden change is there. Like sudden change means earlier something was there and then all of a sudden input has been changed to some certain value. So you might have seen that this one, your step signal is like for example, for some input, step signal is for t is less than 0, your step input is having a magnitude equal to 0, and above t equal to 0, some magnitude is there. So there is a sudden change in input. So step signal represent the sudden change. And constant velocity, like for example, your input is increasing constantly, so that ramp signal will represent the constant velocity. Or if there is a constant acceleration, so that this one parabolic input represents the constant acceleration, means you can test your system in the laboratory by using sudden shock, means nothing but the this one your um, impulse input, or sudden change is nothing but the step input, or constant velocity is nothing but the ramp input, or constant acceleration is nothing but the parabolic input. So that's why this impulse signal or step signal or ramp signal or acceleration signal, all those four signals are considered as a standard test signals in a control system. So this is related to the time domain analysis, but when you are doing the analysis in a frequency domain, so you have to change the frequency. Okay, so you have to change the frequency right from 0 hertz to very high like megahertz or gigahertz and so on. So you have to change the frequency. In that, you have to change the amplitude, you have to change the phase and then frequency and so on. So you know that sinusoidal wave, in sinusoidal wave you can change the frequency, you can change the amplitude, you can change the phase and so on. So sinusoidal signal is also considered as a fifth standard signal. But generally, the sinusoidal signal is used for doing the frequency domain analysis, whereas ramp and this one sudden shock means your impulse signal, or sudden change means your step signal, and then constant velocity means ramp signal, and constant acceleration means parabolic signal. So all those four signals are considered as a standard test signal in a time domain analysis, whereas sinusoidal signal is considered as a standard test signal in frequency domain analysis. So the dynamic behavior of a system is therefore judged and compared under the application of standard test signals, like for example, impulse is nothing but the sudden shock, and step is nothing but the sudden change, and then constant velocity is nothing but this one ramp signal, and constant acceleration is nothing but parabolic signal, and so on. So these are the standard test signals by which we can see the dynamic behavior of the system. So other standard signals are like as I said, sinusoidal signal, which is generally used for doing the analysis in the frequency domain. So first, before starting this time domain analysis, we'll study in detail about the standard test signals, and then after that we'll study the first order system and the second order system and so on, right? So let us start with a standard test signal. So standard test signal, as I said, that sudden change, no, not sudden change, this one, your sudden shock. Sudden shock means you are giving jerk to that system, and you are testing that system under that jerk. So this sudden jerk or sudden shock can be represented by the impulse signal in electrical signal. See that here impulse signal is having some magnitude at t equal to 0. So this your x-axis is t, y-axis is amplitude, and then delta t is representing the impulse signal. So this delta t will be having amplitude equal to a when t is equal to 0. See that when t is equal to 0, at that time this signal is having suddenly amplitude equal to a, and below that t, or if t is not equal to 0, whether it is a minus or whether it is a plus, okay, this amplitude of this signal is 0. So that's why mathematically this impulse signal is represented as delta t is equal to a when t is equal to 0, and this delta t will be equal to 0 where t is not equal to 0. So when a is equal to 1, so this magnitude is equal to 1, if this magnitude a is equal to 1, then so this will be equal to 1 at t equal to 0. So this signal is called as unit impulse signal. Now, particularly this unit impulse signal, for what purpose it is used? Impulse signal, as I said, that impulse signal is used for testing the sudden shock or sudden sudden shock or jerk and so on. Also, this unit impulse signal is used to find out the transfer function of that system. See that, for example, when a is equal to 1 means delta t will be equal to 1. So R of s will be equal to 1 in that case. And you know that C of S by R of S is equal to transfer function. And if you put the value of R of S is equal to 1, means input is your unit impulse, then C of S or your output will be a transfer function, right? So for finding the transfer function of unknown system, you have a black box and you don't know what kind of mathematical system modeling is there, and you'd like to find out the transfer function of that system. Then in that case, you can apply input as a unit impulse input whose magnitude will be equal to 1 when t is equal to 0, and rest of the time it will be 0. And then from that, whatever output you measure, that will give you the basically transfer function of that system, because you know that transfer function is nothing but C of S by R of S, where C of S is the output and R of S is the input. Now, when R of S is 1, okay, so C of S will be directly the transfer function. So to find out the transfer function of unknown system, generally this unit impulse signal is used. Okay, and this impulse signal will be equal to unit when the magnitude of this one is equal to 1. So if A is equal to 1, the impulse signal is called as the unit impulse signal. I hope that you have understood what is by unit impulse signal and where it is used. Okay, and what it signifies for the real world. So for real world, it signifies the sudden shock, okay, or sudden jerk. Okay, and then this is represented as delta t equal to A when t is equal to 0, and rest of the time it is 0. And when A is equal to 1, it is called as a unit impulse signal, and this unit impulse signal is used to find out the transfer function of unknown system, right? Now, second standard test signal is the step signal. Okay, now as I said that we have to test our system for sudden jerk or sudden shock. So generally for that, impulse signal is used. Also, I said that you have to test our system for sudden change. Now, sudden change, which electrical signals signifies the sudden change. So this step signal generally signifies the sudden change. Like for example, this U of t is the representation of the step signal. Then from this graph, you can see that mathematical model of this step signal will be equal to what? So this will be having amplitude equal to A when t is greater than or equal to 0. And it will be 0 when t is less than 0. So there is a sudden change in amplitude of this signal from 0 to A. Okay, below t is less than, when t is less than 0, at that time its amplitude is 0, but when t is greater than or equal to 0, then amplitude is A. So there is a sudden change in amplitude, and when you are like to test our system, design system for sudden change kind of things, then generally we use the standard test signal as a step signal. So the step signal imitate the sudden change characteristic of the actual input, right? So U of t will be equal to A when t is greater than or equal to 0, and U of t will be equal to 0 when t is less than 0. So this is when, see that U of t is equal to 0 when t is less than 0. So this is 0. And when U of t is equal to A when t is greater than or equal to 0. So mathematically, this step signal is represented like this. Another thing is that this step signal can be called as a unit step signal if the magnitude of this step signal is 1. Means if the value of A is equal to 1, the step signal is called as the unit step signal. So generally, your time domain analysis, okay, for testing your system for sudden change, this step signal is used. I hope that you have understood what is by step signal and its mathematical representation of this step signal, right? I hope that you have understood this one. Then the next signal is called as the ramp signal. Okay. Now, as I said that we have to test our systems for different input, like as a sudden jerk or sudden shock. So impulse input will represent that one. Then sudden change, the step signal will represent that sudden change. Okay, the next one is the constant velocity, right? So the constant velocity is represented by the ramp signal. See that this is the ramp signal. So your x-axis is t, y-axis is your r of t, and then the ramp signal imitates the constant velocity characteristic of the actual input signal. Now see that this velocity is going on increasing. Okay, and this basically there is a constant velocity. If you calculate the constant velocity, velocity, it will be always constant. So r of t will be equal to, so mathematical, when you are representing this signal, so this mathematical model of the signal will be equal to r of t is equal to a of a into t. So this basically amplitude. So this magnitude is basically a into t, and then this is when t is greater than or equal to 0. For t is less than 0, what is the magnitude of this one? It is 0. So that's why it is mentioned as a 0. When t is less than 0, it is called as a it is a 0 magnitude, and its magnitude will be equal to a into t when t is greater than or equal to 0. Now when this value of a is equal to, see, this is nothing but the slope of that line. So this, you know that how to find out the slope of the line, y2 minus y1 divided by x2 minus x1, right? So y2 means this one. So if this is equal to, like, for example, if this is 1 and this is also 1, okay, then you'll get the slope is equal to unit slope. So if the value of a is equal to 1, the ramp signal is called as the unit ramp signal. See that. So this, you see that at 1, when t is equal to 1, this is a, and this value of a is equal to 1. Okay, if value of a is equal to 1, so this y-axis coordinate will be 1, x-axis coordinate is also 1. So y2 minus y1, so here y1 is basically 0, x1 is 0, so y2 is basically 1, x2 is also 1. So x2 by y2 will be equal to 1. So your this one slope will be equal to 1, and that is called as the unit slope, right? And then this unit slope signal is nothing but the unit ramp signal, is called as the unit ramp signal. Now when basically at 2, this, if a is equal to 1, then this will be 2. So 2 at 2, y-axis is 2, x-axis is 2, so this is also having a slope equal to 1, and so on. So this signal is called as the unit ramp signal, right? Now see that so this is the unit ramp signal, basically 1 1 2 2 and so on. So this ramp signal signifies the constant velocity. So velocity remains constant, which is equal to 1, right? Which is equal to 1. So basically slope, okay, and this slope is 1 basically, and then ramp signal is called as the unit ramp signal. So when you like to test your system for constant velocity, then at that time you have to use the unit ramp signal as an input to that system, and then you have to see the behavior of that system. You have to measure the time response parameters as well as steady state parameters and so on, right? The last signal which is used here is the unit acceleration signal or constant acceleration signal and so on. So you know that the parabolic signal, which is represented like this, like as a parabolic. So P of t represent the parabolic signal, and then this your x-axis is time axis, and y-axis is your amplitude. So this parabolic signal imitate the constant acceleration characteristic of the actual input signal. So this is the constant acceleration. Basically, if you calculate the acceleration, it will be always constant. So mathematical model of this signal is given by P of t is equal to at square by 2. Okay, when t is greater than or equal to 0, and this will be 0 when t is less than or equal to 0. If the value of a is equal to 1, at that time this signal is considered as a unit parabolic signal, right? So when a is equal to 1, then this is called as the unit parabolic signal. Now see that when a is equal to 1, so it will be unit parabolic signal and so on, right? Then this one. So this is unit parabolic signal, all right? Okay. So I hope that you have understood the basically 4 standard test signals which are used. Why they are called as the standard signals? Because they represent the this one system, basically sudden shock or constant, okay, this one sudden change, and because we would like to test our system for the sudden change or sudden shock or constant velocity and constant acceleration. So sudden shock is imitated by your impulse response or impulse signal, and then sudden change is imitated by your this one step signal. Constant velocity is imitated by your ramp signal, and constant acceleration in the electrical system is imitated by your parabolic signal. So you can test those systems in a laboratory with these signals, and that's why it is called as the standard test signal. Now look at the relation between the this signal. Like for example, you have if you take the derivative of this signal, right? If you take the derivative of this signal, you will get what kind of signal? If you take the derivative of unit step signal, you will get the this one impulse signal, right? Similarly, if you take the derivative of this signal, you will get the step signal. So step signal, basically ramp signal or step signal is a derivative of ramp signal, or you can say ramp signal is an integration of step signal. Or if you go back, this one, if you integrate this impulse signal, so this integration of this impulse signal is nothing but the step signal. So like that, for example, if you integrate this entire unit step signal, your unit impulse signal, you'll get the step signal. Similarly, if you integrate this one a step signal, then you will get the ramp signal. Or if you integrate the ramp signal, you will get the parabolic signal, and so on. So these are the relationship, or basically if you take the derivative of this parabolic signal, you will get the ramp signal. If you take the derivative of ramp signal, you will get the step signal. If you take the derivative of step signal, you will get the this one your impulse signal. So as I said that generally impulse signal is used to find out the transfer function of unknown system, and then the step signal or ramp signal and then parabolic signals are used for testing that system for sudden change or sudden constant velocity and constant acceleration and so on. So that's why all those 3 signals are considered as the standard test signals. Okay, so tomorrow we'll continue with this one, the Laplace transform of this signal, and after that we will start the first order system. So if you have any doubt about standard test signal, you can ask, otherwise we'll call it a day. So over to you.